Thank you, Davide. So I'm César Fuguet from CA in Grenoble, in France. And I'll talk about an IP that we designed in CA. So it's called the High Performance L1 Data Cache, HPD cache, for RISC-V cores. It's already in the OpenHW group catalog of IPs. So actually, we are working also in this IP during the TRISTAN project, and we are improving its quality to reach TRL7 level, right? So a short outline of the presentation. So first I talk about why we did this IP, the architecture. We have actually silicon prototypes, FPGA prototypes of it. Talk a little bit about performance, so difference, the speed up we gained with this IP with respect to the original write-through cache that it's with the CVA6 core. We'll talk about a little bit about verification, project status in the OpenHW perspective process of submitting an IP, some planned new features that we will add during the TRISTAN project, and finally some conclusions. So first, motivation. So the first thing to know is that in HPC systems, normally applications, the bottleneck for performance is actually memory accesses. And memory caches, or cache memories, are actually an essential component to hide the latency of the memory and actually enable good performance in scientific applications, or HPC applications. So as we can see in modern memory subsystems like HBM for high bandwidth memory, they actually offer very high throughput, so you can have a lot of memory operations being processed during a given time, but actually the latency for the first request you get there is quite important. So we're talking about hundreds of nanoseconds, okay? So that's why it's important for HPC caches to actually being able to overlap a lot of requests to the memory to hide this memory latency. And that's the main point of the IP that we are putting in open source in the OpenHW group. So let's talk a little bit about architecture of the cache. So there is a bunch of features there. So you have the cache in the middle. In the upper side, you have requesters. These requesters are actually either cores, RISC-V cores, or accelerators, for example. You can actually have several request ports. It's a configurable number of request ports. Each of these ports are also configurable in terms of data bandwidth you need for your accelerator. For example, you can have some ports using 64 bits for the load store unit of your core, but you can also have, if you have tightly coupled accelerators in your core, you can have, for example, 256 bits data width for those if you need a very high bandwidth. So we have a programmable memory hardware prefetcher inside of it. We have a it's actually a write-through cache, so there is a write buffer to be able to decouple the acknowledgement from the memory to the acknowledgement of the core, so enable out of order and outstanding performance. So this is one of the main features also, is that it supports a very high configurable number of in-flight miss requests to the memory. And actually this is what enables to the hiding of the memory latency to the core itself. We have adapters for the network on chip using AXI, for example. We actually allow out-of-order execution of memory operations. The idea is that if you have a requester that sends first a memory operation, a second one, and this second one depends on the completion of the previous one, instead of stalling the core, we actually put it aside in a replay table, and we keep processing new requests, right, to hide latency. And then when the conditions are met to handle the requests that are being set aside, then we can execute them. Regarding the kind of operations that we support, so it's normal load stores. We also support cache management operations, CMOs, and atomic operations. So this cache has been, for the moment, integrated to the CVA6 core. Actually, it's just a comment here is that it's a cache that is meant to be portable to other cores. For example, an out-of-order core will benefit much more of this cache, but anyway, you can actually benefit from its features using an in-order core like the CVA6. Okay, so this is just mention a little bit what are the modifications we did on the CVA6 core to benefit from the cache, right? So first modification for the so the current version of CVA6 can only forward a single load request to the memory. If there is a miss, the load unit will be stalled. So I made a modification to add a table that allows you to have several in-flight loads to the cache, to the memory. So actually this is not yet merged in the CVA6 repository, but should be there soon. There are other modifications. We actually introduce ID signals in request and response interface to the cache. The idea is that as you can have several load requests to the memory, the responses can be out of order, right? So because if, for example, if you do a first load that misses on the cache and then a second load that hits on the cache, the second one will be acknowledged before the previous one. So you need to be able to identify which, to which request the response corresponds. So this is already merged in the CVA6 repository. You have the PR, the pull request numbers there. So I follow actually the process that Davide was explaining at the beginning of the presentation. So I did a fork of the CVA6. I made modifications on my fork CVA6 repository. I pushed there, then a pull request on the CVA6 repository. And yeah, so most of these modifications are already merged. There is a pending request, a pull request to actually add the HPD cache as one of the possible cache subsystems in the CVA6. There are a lot of modifications currently in the parameterization of the AXI interface to be able to choose the data width of the AXI bus and number of bits of the ID signals, etc. So that there are some open pull requests on that subject. And there is also a small adapter between the load unit, or actually the load store unit of the CVA6 and the cache to adapt the interface. And that's what it's important to get from this presentation, is that you can actually adapt this cache to other cores with a given adapter between both of them. So we have some silicon prototypes, some FPGA prototypes. Actually, this cache was developed during the EPI project, European Processor Initiative, a first version of it anyway. It was developed for our in-house accelerator that is called the VRP, for Variable Precision Accelerator. It's actually a RISC-V base core. We forked from the CVA6 core and we added a custom instruction set for do computation on variable precision floating point numbers. Actually, it's an accelerator that can process or can do computations on floating point numbers with a 512 bits mantissa, from 32 bits to 512 bits mantissa with steps of 8 bits. It's for some kind of HPC application. We actually have a publication on that subject, so if you're interested, you can go there. And so during the EPI project, the EPI project, we did 2 silicon tape-outs. So the first one is the EPAC 1.5. It's a tape-out in Global Foundries 22 nanometers technology. So you have the VRP in the bottom side of the chip, and the VRP is using this cache. And there is a second tape-out that is not yet done, but it will be done in the next month. I don't know if you have heard about the Cyber company that is fabricating a general purpose processor on TSMC7 technology. So actually we have a bunch of ARM cores, so 82, if I remember well, ARM cores, and there are 2 tiles, each with 4 VRP cores implemented this cache. And this is in TSMC7 technology. And of course we have in-house FPGA demonstrators to validate the cache, validate the VRP, and run actual applications in it. So I will not go through all the parameters, but the ones that are important, for example, is that the cache in those prototypes support up to 128 miss requests to the memory. So Actually, we have HBM in this prototype here, and we can have hundreds of cycles of latency to get an actual data. So that's why we need 128 miss requests to actually be able to do computation while we are bringing the new data to the core, to the cache. And as I said at the beginning, so we have some ports with 64-bit data width for the core itself, for the load store unit of the core, because it's a CVA6, so 64-bit core. And then we have 128 bits data width for the VRP accelerator, because it is actually a data-intensive accelerator. Well, I will not go through all of that, but the important thing, so if we compare with the original write-through cache, so both of them are written in System Verilog. And the most important differences is that first, for example, we have these deep configurable mis-status holder registers to support multiple miss requests to the memory. We have a hardware memory prefetcher. The hardware cache coherency actually is already implemented in the original write-through cache using the OpenPython cache coherency protocol. And we are actually working on also adding the OpenPython support for the HPD cache. There is already a work on that. And what we need to have from this presentation actually is a very configurable cache. Request ports can go from 32 to 512 bits of data width on the request port. We can also change the width of the write buffer entries to support write coalescing and have very large data to the NOC. And we have this out of order execution to prevent the core from being stalled, right? Yeah, so this is a small comparison between the original cache and the new one. So it's a work in progress, or we are actually running right now a lot of different benchmarks to get more information about it. But so this is an execution of the sparse matrix vector multiplication. Is a very common workload in HPC systems. And what we can see is that, so we have here, so in the bottom, in the x-axis, you have the latency to the memory. So actually, I'm running the application 3 different times. One with 20 cycles to access the memory, external memory. The second one with 40 cycles, and the third one with 80 cycles. And then on the y-axis, you have the instruction per cycle of the core. So as we can see, we have 15% better performance than the original cache with 20 cycles, 20% with 40 cycles, and 27% better speed up on 80 cycles. Regarding so this is a comparison of resources. Actually, so this was a cache that was meant for ASIC, but so for the moment, I don't have any ASIC implementation of the original cache, so I cannot do a comparison for the moment. So I tried to do a comparison on FPGA resource utilization. We can see that in terms of logic, so lookup tables is roughly the same. So we are 0.3% worse than the original one. In terms of flip-flops, we are 17% worse, but we are better in ramps. And so this is it's a work in progress, because as I said, so it was a cache that was meant for ASIC. So there are some structures there that can actually be in RAM and are currently in flip-flop. So at the end, I think will be roughly the same. Of course, we have more because there is no free lunch, right? So more performance, you need to add some more hardware in your design. But it should be roughly the same, at least not that important as shown there. Next slide, please. So this is actually a comparison with the HPD cache and the HPD cache using the hardware prefetcher. So I'm comparing the same cache, the new one. I'm running the dense matrix vector operation. And what we can see is that, so again, we have 20, 40, or 80 cycles latency to the memory and the instruction per cycle on the y-axis. As we can see, when we activate the hardware prefetcher, we get 55%, 209%, 319% better performance than when we run the same program without the hardware prefetcher. And as you can see, so you have the same instruction per cycle when you activate the hardware prefetcher. So he's doing his job, right? So it's when each time the core is actually accessing the data, it's always in the cache because the hardware prefetcher it's looking for that before the actual access from the application. So yeah, for this cache we want industrial grade quality, high quality IP. So for that we need to do intensive verification, as we already listened at the beginning of the presentation from Mike and Mario. So we are actually targeting TRL7 for this IP. This means that we are working on a very detailed specification. Actually, it's already there in the Git of the cache. We also have very complete UVM test bench environment to test the cache that will be actually open source at the end of somewhere during the project or during the TRISTAN project. And so we are working on test plans currently, working on requirements, but the environment is beginning to be there. So the project status, so if you remember the process that Davide showed at the beginning, so we already passed the two first gates of the project. So we did the project concept, then project launch, and the next gate is plan approved. So normally we have all the information to do the plan approved document, so that will be done soon. But actually the cache itself is already in the Open Hardware Group IP catalog. So you can get it from that link there or scanning the QR code. So it's in the Open Hardware GitHub repository. So we already have a user manual there, very detailed one. We are writing requirements, test plans during the TRISTAN project. And we, of course, we are doing still some development to improve the cache. So we are debugging the CVA6 integration while running Linux, because actually until now the VRP worked in bare metal, so we were not activating the MMU. Now it's currently been done on debug. So we are submitting the pull request that I showed at the beginning to integrate the cache to the CVA6. We are doing microarchitecture optimizations. We are evaluating the performance of the cache and the area, also in two different ASIC technologies. And in the short-term objective, is to actually have the complete integration on the CVA6, so you can clone the CVA6 repository and have both the new cache on the CVA6, and you are able, through configurations, to use this one instead of the original ones. We are focusing in TRISTAN to make a TRL7 for this IP, but we are actually also adding new features to the cache. So the first one is to support hybrid write policy. So currently it's write through, but we wish to support both write through and write back, and not actually in the entire cache, but you can actually choose for a given set of cache lines to be write through and for another given set of cache lines to be write back. This is actually very good for if you are in an embedded environment, you can reduce a lot of power consumption. For example, if you are all the stack, for example, the stack segment, you put it in write back, but all the data that is shared with other cores in your system, you can put it in write through. And that way, so you win a lot of power consumption, because most of the writes in your system are actually in the private part, so the stack part, and there is only a few writes in the share part that will be write through. There is also a scratchpad mode. So this is for predictability, so for safety and security applications. And as I said, so the test bench will be open source, available in the Open Hardware Group repository. There's a work in progress adding the Open Python cache coherency protocol support on this cache. Actually, this has been done during a Google Summer of Code that I'm commenting with Jonathan Balkin, the designer of the Open Python cache coherency protocol. And we plan to add support for ECC and internal SRAM, again, for safety security applications. Now we are in the conclusion. So we are contributing this cache to the Open Hardware Group. We are targeting high quality, so industrial companies can actually put it in their products if they are willing to. So it's a highly configurable cache to support different PPAs, power, performance, area trade-off. It's actually the first CA open hardware source that we are contributing. So it was very intensive process for me, because CA was not used to do this kind of stuff. So there are a lot of barriers, right, to get it done. But at the same time was very, very good, because so the open hardware community is amazing. A lot of discussions on different channels, a lot of feedbacks. So it's a very, very good experience for anyone. And so we have prototype DHPD cache in silicon, FPGA. And as I said, so we are targeting TRL7 and adding new features to it. So thank you very much.